All right, we're going to continue on with seeing how to reduce Boolean expressions. So we're going to start off by looking at a few more examples of some algebra theorems. And then we're going to do some expressions, examples of how we reduce. All right, so let's start off with saying we have an OR gate that on one path is X and Y. And then the other path would be X with a Y bar. All right, so what we need to look at is, from some voltage, what is it that really depends on in these two paths for our output? All right, so to understand this, let's look at two cases. Let's look at the cases of what happens when first y is equal to 0. So when y is equal to 0, we have x. We're going to have the top one open. We're going to have x. And then the bottom item will be closed. And if we look at this, we're going to see that the voltage could only flow through the bottom. And if it only flows to the bottom, it depends on x. The other case, it could be y is equal to 1. If y is equal to 1, we have x. Then we have the top closed. We have x, and then we have the bottom open. We have the same thing that's going to happen. We have to flow through the top. And in the top, it depends on x. So at that point, we can say, if I had the expression x ended with y, or x ended with y bar, all we're really concerned about is x. All right, so now let's look at something a little bit different. Let's look at, I have an x, I have a y. That's going to be ORed with an x and a y bar. Okay, and this would be our output z. Well, what would be some options that we would have? Well, options again, let's say y is equal to 0. If y is equal to 0, we have x on the top part. We have open on the bottom part. I have x on the top part. I have a close on the bottom part. So the possible flow would be, I could flow this way. That depends on x. Or if we say y is equal to 1, I have x, I have closed, I have x, I have open. The flow would be, I go through the bottom and then I go through the top. It depends on x. So our expression would be x or y, and then with x or y bar, all we really depend on is x. Okay, so let's do another one. And let's say I have an OR gate, I have x on top. The second path, it is an x and a y. Well, in this path here, both of these would need to be 1 to have voltage flow through the bottom part. And all I depend on is x for the top part. Well, since x is in both pieces, really that's if the top is true, I don't need to worry about the bottom half. So then I can say, well, x plus x and y is just x. Same thing would be if I had it as an AND gate, x going into x or y. So in this case here, if I flow this way, if x is closed, I still flow on the x side. The y is not important. So it'll be x is just a reduction. Okay, the next one is, let's say we have a y, and then that's followed with an x and a y bar. Okay, so we have y and then with x or y bar. What reduction are we going to see? Well, if this is closed, this one will be open. That's the only way we can start flowing this way. But if that bottom half is open, I depend on the top half. So I could say, I could take out that entire y bar. It would just be xy. Next item we can have is, I have an x and it with a y bar. Then I have a y at the bottom. So I have x, y bar plus y. Well, what would this be equivalent to? Well, it's equivalent to if the bottom part is closed, the top part is open. I only go through that bottom part. If I had this top part closed, the bottom part is open, I can only flow through the top part. Well, I don't need both the y and the y bar, because if I know y is open, I know the top part is closed. I can just say that's the same as x plus y. Because if the bottom is open, the top has to be closed. All right, so now that we did a couple more theorems, let's see if we can do some type of reductions. All right, so let's say we have an expression z, and z is a bar bc plus a bar. So when we draw this out, I put the little dots there. They're not necessary. We can just do it as a bar bc plus a bar. We're going to kind of say that and is like a multiply for us. Okay, so we got to set this up to see what kind of reduction we can do. Well, we can see that both terms have an a bar. So let's substitute x for this term. And then I'll leave this bc as y. So I got xy plus x. Okay, so let's scroll up and let's see if we find that. Xy, that's xy bar, so it's not that one. Here we go, xy plus x. And that turns out to be x. Well, then we substitute back in our x. Our x was a bar. All right, let's do another example. let's say I have Z is A or C or D, that quantity ended with A or C plus a D bar. Okay, so I'm going to look at these terms and see, do I have anything in common? Yes, I got this A plus C. So let me take that A plus C and I'll put that as an X. So I'm going to have something end with something. Okay, I have a plus. I can bring down that plus. The D, I'll make that a Y, and then I have a D bar, so that's a Y bar. Okay, so I got X plus Y ended with X plus Y bar. Okay, let's go up and let's see if we find that. So we got X plus Y bar. That turns out to be just X. So all that is equal to X. What was our X? Our X was A plus C. So that's our reduction, A plus C. All right, let's do another one. Let's say I have Z is AB plus C ended with B bar D plus C. C bar, let's do C bar, and AB plus C. All right, so we're going to look for stuff in common again. I have an AB plus C, an AB plus C. Let's make that X. Okay, and then I'm going to have this BD plus C bar. Let me make that Y. So I got XY plus X. I think we did that one already. Yes, we did here. XY plus X. That's just X. And X was our AB plus C. So that's the reduction that we would make. Okay, let's do one more. Let's say we have Z is B plus C, BD plus B plus C bar. All right, so I'm going to look at B plus C, and I got a B plus C bar. So I'm going to take this as being X. I'm going to take that one as being X bar. And the BD, that would be Y. Okay, so I got XY plus X bar. All right. So let's see if we have that XY plus X bar. Let's go up to our theorems. So here we get something similar. This is XY bar plus Y. So let me copy this. And then let's take that down and see what we have. All right, so if we look at this, we have an X bar, we have an X, we have a Y. It's almost the same setup. So let me do a little change here. Let me cross these out. Let me pick a different color to cross out with. So let me cross out these items, and let me make it match. Let me say that B plus C bar, let me make that Y, which will make B plus C a Y bar, and then I could do BD as an X. And then I got X, Y bar plus Y is equal to X plus Y. So this is the final term I'm going to have. Well, what is X? X is what's bracketed in green, which is BD, plus what's my Y? My Y here is B plus C with a bar. So sometimes you'll have to kind of figure out what the correct substitution will be. So here, the bar is our term without a bar, and then the one without a bar is the bar term. So there might need to be a little bit of manipulation that you will have to do. All right, so that's some more simplification. In our next video, we're going to look at two forms of an algebra expression called sum of products and product of sums.